Geographic Information System. Triangular irregular network. In this chapter, we will be discussing about the triangular irregular network, the Delaunay triangulation, sources of tin, mass points, break lines and hulls, polygon surface types, usage of tin, advantages and disadvantages, terrain data set. The triangulated irregular network TIN is a digital data structure used in a geographic information system for the representation of a surface. A TIN is a vector-based representation of the physical land surface or the sea bottom, made up of irregularly distributed nodes and lines with three-dimensional coordinates, that is x, y and z, that are arranged in a network of non-overlapping triangles. TINs are often derived from the elevation data of a rasterized digital elevation model, that is DEM. The first triangulated irregular network program for GIS was written by Randolph Franklin at Simon Fraser University in 1973. A triangular irregular network of a DEM refers to a digital elevation surface that is represented not as a grid, that is by pixel, but as a connected series of continuous non-overlapping triangles. The triangles are made from a set of points called mass points, and within each triangle the surface is represented by a plane. The more mass points and more carefully collected, the more accurate the model of the surface. The TIN represents one of the digital data structures used in geographic information system for the representation of surfaces. The remainder of this note is discuss various applications of DEM. The remote sensing methods used to measure heights of creating a DEM, the necessary planning for generation of a DEM, that is the mission planning, and the quality aspects of DEM creation and usage. TINs have been used by the GIS community for many years and are digital means to represent the surface morphology. TINs are a form of vector-based digital geographic data and are constructed by triangulating a set of vertices or points. The vertices are connected with a series of edges to form a network of triangles. The edges of a TIN form contiguous, non-overlapping, triangular facets and can be used to capture the position of the linear feature that play an important role in the surface, such as ridges, lines or the stream courses. The graphics show the nodes and the edges of the TIN and the nodes and edges and the faces of a TIN. There are different methods of interpolation to form these triangles, such as the Delaunay triangulation or distance ordering. ArcGIS supports the Delaunay triangulation method. The Delaunay triangulation is a proximal method that satisfies the requirement that a circle drawn through the three node of a triangle will contain no other node. Delaunay triangulation has several advantages over other triangulation methods. The first, the triangles are equiangular as possible, thus reducing the potential numerical precision problems created by long skinny triangles. Second, ensures that any point on the surface is as close possible to a node. Third, the triangulation is independent of the order the points are processed. The result of triangulation satisfies the Delaunay triangular criterion, which ensures that no vertex lies within the interior of any of the circumcircles of the triangle in the network. If the Delaunay criterion is satisfied everywhere on the TIN, the minimum interior angle of all triangles is maximized. The result is that long, thin triangles are avoided as much as possible. A triangulated irregular network surface can be generated from either surface source measurement or by converting other functional surface into tin surface. The input feature used to create a tin remain in the same position as the nodes or edges in the tin. This allows a tin to preserve all the precision of the input data while simultaneously modeling the values between known points. We can precisely locate features on a surface such as point, line or a polygon that contain elevation information. Use points as spot location of elevation data. Use lines with in-height information to enforce natural features such as lake, streams, ridges and valleys. Finally, use polygons to clip the tin to area of the study. A tin surface can also be created from other functional surfaces such as raster or terrain dataset, but raster surface need conversion to a tin to add additional features such as streams and roads to a surface model. To convert a raster dataset to a tin, use the raster to tin geoprocessing tool. Several different vector data sources can contribute to a tin surface. As part of tin surface design, you can establish the role of each data source in the tin and how each data source is used. Mass points are point height measurements. They become nodes in the triangular network. Mass points are the primary input into a tin and determine the overall shape of the surface. The tin allows the model heterogeneous surfaces efficiently by including more mass points in an area where the surface is highly variable and fewer in places where surface is less variable. The example shows the mass point categorized by the height of the attribute. You can see the area towards one side is having less amount of mass point, whereas the area present to the other side has more amount of mass points. Break lines are lines with or without height measurements. They become sequence of one or more triangle edges. Break lines typically represent either natural features such as ridge lines or streams or built feature such as roadways. There are two kinds of break lines, hard and soft. Hard break lines. Hard break lines represent a discontinuity in the slope of the surface. Streams and road cuts could be included in a tin as hard break lines. Hard break lines capture abrupt change in a surface and improve the display and analysis of tins. Soft break lines. Soft break lines allow to add edges to a tin to capture linear features that do not alter the local slope of a surface. The study area boundaries could be included in a tin as soft break lines to capture their position without affecting the shape of the surface. Halls. Polygons represent surface feature which areas such as a lake or a boundary of a separately interpolated areas. Halls could define the shore of an individual island in an archipelago or the boundary of a study area. There are four polygon surface feature types are present. First, the clip polygon. Clip polygon interpolation define a boundary for a tin surface. Input data that falls outside the clip polygon is excluded from the interpolation and analysis operation. For example, the contour or volume calculations. Erase polygons. Erase polygon define a boundary for interpolation. Input data that falls within the erase polygon is excluded from the interpolation and analysis operation, for example, contouring or volume calculations. Third, the replace polygon. The set of boundary and all interior heights to the same value. A replace polygon would be used to model a lake or an area on a slope excavated to a level surface. Fourth, fill polygons. Fill polygons assign an integer attribute value to all the triangles that fall within a fill polygon. The surface height is unaffected and no clipping or erasing takes place. Polygon features are integrated into triangulation as close a sequence of 3 or more triangle edges, including break lines and polygons in tin, which gives more control over the shape of the tin surface. To get the sense of difference between the break lines can make in a tin. Compare the surface created from the mask point alone to the surface created from the mask points and break lines. Tin models are less widely available than raster surface models and tend to be more time consuming to build and process. The cost of obtaining good source data can be high, and processing tin tends to be less efficient than processing raster data because the complex of data structure. Tins are typically used for high precision modeling of smaller areas, such as in engineering application, where they are useful because they allow calculation of the panmetric area, surface area and volume. An advantage of using a tin over a DEM in mapping and analysis is that the points of a tin are distributed variably based on the algorithm that determines which point is most necessary to an accurate representation of a terrain. Data input is therefore flexible and fewer points need to be stored than in a DEM with regularly distributed points. While in tin may be less suited than a DEM raster for certain kinds of GIS application, such as analysis of a sloped surface and aspects, tin have the advantage of being able to portray terrain in 3 dimensions. However, tins have a disadvantage and are not suitable for every project. When using tins, details on the actual triangles may be lost. Also because tins are the linear, many edges will appear jagged, distorting the image. Tin has the ability to describe the surface at different level of resolution. Tin has the efficiency in storing data. Disadvantage is in many cases tin require visual inspection and manual control of the network. Remotely sensed elevation data such as LiDAR, sonar point measurements number in the hundreds of thousands to hundreds to millions. Managing and modeling this type of data is cumbersome for most hardware and software available today. The terrain dataset allows a series of rules and conditions to be generated that index source data into an ordered set of tin pyramids, that is generated on the fly. Terrain datasets are an efficient way to manage large point-based data in a geodatabase and produce a high-quality, accurate surface on the fly. LiDAR, sonar and elevation measurements can number from several 100,000 to many billions of points. Organizing, categorizing and generating a 3D product from these type of data is difficult at best and prohibitive in many cases. Terrain dataset allows you to overcome these data management hurdles, edit your source data and produce highly accurate tin at varying resolution. Rendering very large tin is generally difficult, partially due to the limitation by hardware such as video cards. However, terrains are beneficial in that when you render the areas that you need to visualize at an optimized resolution. Thus, if you have a small scale area in an arc globe or arc map, the fewer nodes will be utilized to the terrain to generate the tin rendering on your screen. However, if you zoom in to an area at large scale, a full resolution utilizing all nodes of that area will be used to generate a tin on the fly. Obvious advantage is that only a small portion of the study area is being rendered with large number of nodes, or a subsampled collection of nodes is used to generate a lower resolution tin on the fly. Terrains reside in feature data sets in personal, file or ArcSDE geodatabase. The other feature classes in the feature data set can participate in the terrain or actually be embedded in the terrain, which means that the source data could be moved offline after the creation of the terrain dataset. The graphic illustration of how the multiple types of feature classes can be participate to generate the tin pyramids. An example of multiple source data participating in variable resolution tin pyramids, that is the terrain data sets, are unique in that they can either embed or reference the source data. Through the indexing of each point measurement, and a set of tin pyramids is generated, each set with successive fewer participating nodes, that is the source points. This allows the arc map and arc globe to generate a tin on the fly at whatever resolution is needed for the scale of the viewer. These are some of the primary benefits of the terrain data set. First, the ability to store and manage vector-based terrain information in the geodatabase. Second, scalable and seamlessly collection can reach into the billions of points. Third, the terrain pyramids enable appropriate subsets beside on an area of interest and accuracy requirements to be retrieved quickly through optimized database query. Pyramids offer a form of scale dependent generalization that is based on known vertical or horizontal resolution. Fourth, the ability to be modified over time. Fifth, edits are local and do not require rebuilding the entire model. In ArcSDE, terrains can be versioned. As with other data types, versioning offers a powerful approach for editing data and deriving what-if scenarios in multi-user environment. When using ArcSDE, terrain datasets enable centralized management and multi-user access to large data collection, a capable platform for raster digital elevation model production, high quality interpolation designed to handle a wide variety of input data types, data thinning tools to eliminate irrelevant and redundant samples, terrain layer for interactive display and query of the terrain surface. The layer surface representation updates itself automatically as you pan and zoom around the display. Tins are built on the fly based on measurements and level of detail information stored in the geodatabase. Supported geometry, points, multi-points, lines and polygons. Supported data types, stereo captured photogrammetric feature, bare earth LiDAR, first all written LiDAR sonar, bathymetry data. Terrains use tin data structure to represent surfaces. A terrain dataset is a tin based dataset that uses geodatabase feature classes as data source. A triangulated irregular network is a data structure used to model surfaces such as elevation as a network, as a connected network of triangles. Tins are assembled from a series of data points with x, y and z values and partition geographic space into continuous non-overlapping triangles called faces. The nodes of each triangle are elevation or surface points. Each triangle node has an x, y coordinate and a z surface value. Any surface value can be interpolated within a face or along the edge. Terrains use pyramids to represent multi-level of resolution. A terrain dataset is a multi-resolution tin. It has a series of tins, each of which is used within a specific map scale range. A coarse grained tin is used to large map extents, such as when you are zooming out an entire study area. A file based tin has an effective size limit. The maximum allowable size of a tin varies relative to free continuous memory resources. The largest size achievable under normal operating condition with Win32 is 10 to 15 million nodes. Regardless, it is strongly recommended to cap the size at a fewer millions for the sake of usability and performance. Anything larger than this is best represented using a terrain dataset. More surface points and increasing level of detail are used when you zoom in or focus on larger map scales and specific map extents. As a part of process of creating a data set, you will be define a number of pyramid levels, a working range of map scales for each pyramid level and the relative accuracy of each pyramid level. Two methods exist for creating pyramid levels. One is the Z tolerance and the window size. The level of detail for each pyramid level is defined by the Z tolerance or window size that you want to work with at map scale. Triangulated irregular network represents a topographic elevation surface by a tessellation of non-overlapping triangles with elevation at their corners. Three-dimensional visualization are readily created by rendering of the triangular facets. In regions where there is a little variation in surface height, the points may be widely spaced, whereas the areas where more variation of height, the point density is increased. A tin is typically based on a Delaunay triangulation, but its utility will be limited by the selection of input data points. That is, well chosen points will be located so as to capture significant changes in the surface form, such as topographical summits, breaks in the slope, ridges, valleys, floors, pits and cols. It is technically possible to generate a tin with overlapping facets. Such tins can be more useful for modeling certain geographical features, including overhangs, caves. However, not all GIS packages are designed to handle. The portion of a tin that does not self-overlap is sometimes referred to a functional terrain. Although usually associated with three-dimensional data, that is x, y and z, and topography, tins are also useful for the description and analysis of horizontal distribution and relationships. A tin used to represent terrain is often called a digital elevation model, which can be further discussed used to produce digital surface model and digital terrain models. An advantage of using a tin over the raster digital elevation model in mapping and analysis is that the points of tin are distributed variably based on an algorithm that determines which points are most necessary to create an accurate representation of the terrain. Data input is therefore flexible and fewer points need to be stored than in the raster DEM with regularly distributed points. While a tin may be considered less suited than a raster DEM for certain kinds of application, such as analysis of surface slope and aspects, it is often used in CAD to create contour lines. A DTM and DSM can be formed from a DEM. A DEM can be interpolated from a tin.